Okay, the topic that we are starting is sound and waves. First of all, can you tell me, give me rough idea on what is sound? Sound is, we can say, a disturbance that is traveling in the form of waves. Basically, what is a wave? Wave is simply a disturbance traveling through a medium. Uh, I will tell you what to write and when to write. You just pay attention to what I'm listening and you just look at your screen. Okay. So sound basically is a form of disturbance. It's traveling through a wave. Then waves is disturbance traveling through a material medium. Then there are different kind of waves. Waves we can classify. Okay. One is the waves that we can take it as mechanical waves. And the second kind of waves that we can take is electromagnetic waves. Now, mechanical waves will be requiring a material medium to travel, while electromagnetic waves do not require any material medium to travel. They can travel through vacuum also. Example of this is light. And all electromagnetic waves like ultraviolet, infrared, these all are going to be coming under electromagnetic waves. Light is one of the examples of electromagnetic waves which comes in the visible region. Now, mechanical waves will travel, it will require material medium. It means they can travel only through either solids, liquids, or gases. Now, these waves, electromagnetic waves, are always transverse waves. Mechanical waves can be of both. They can be longitudinal waves. They can also be transverse waves. Now, what is the difference between these longitudinal waves and transverse waves? Basically, it depends on the direction in which the waves are traveling and the direction in which the particles or the disturbance is vibrating. I'll just give you an example. Afterwards, there is going to be a diagram also, and there is also going to be some of the differences which we are going to which are going to be there, and also some basic definitions are going to be there, which we are going to consider in waves. First of all, okay, so this is the first part that you are going to write down, not right now. I'll give you time. The waves, the definition is a disturbance traveling through a material medium in the form of vibrations. Right. The next part which is there, the types of waves. I've already shown you there are two types of waves, basically classification. Now, for Slinky, Slinky is an example which you can take it how these longitudinal waves are going to travel. You can just have a look at this video module and we will see how these waves are going to travel. You can see over here how these vibrations, the particles are vibrating here left and right like this. Okay. So any particle which is there, these particles are vibrating left, right, left, right, left, right like this. And the disturbance or the wave is also traveling in the same direction. So this is an example of longitudinal wave. Now, in case of longitudinal waves, the particles of the medium vibrate in a direction parallel to the direction in which the waves are traveling. This is the definition of longitudinal wave. I'll just give you later to write down the definition as well as all the differences, even the diagrams which you are going to take down for longitudinal waves as well as for transverse waves. And then we'll come, of course, to the other definitions that are involved in longitudinal waves and transverse waves. The next part that is over here. Yes, this is the diagram for longitudinal waves. You can see over here, as you had seen in that video module, the disturbance is traveling in the horizontal direction, while the particles, vibration of particles is also taking place left, right, that is along the same direction. Example of these longitudinal waves, which is also an example of mechanical wave, that is the sound wave. Now we come to the next type of wave, which is there, that is transverse wave. Okay. Now here for transverse wave, you will be able to see over here, the particles of the medium are vibrating up and down like this in the vertical direction, while the wave is traveling in the horizontal direction. It means the angle between both of this is how much? 90 degrees. Okay. So the direction in which the particles are vibrating and the direction in which the waves are traveling, both of them are perpendicular to each other. Okay, example of transverse wave is light wave, which is also an example of electromagnetic wave. In electromagnetic waves, all waves are going to be transverse waves only. They are not going to be longitudinal waves. Okay, so this is the diagram and the part that is there for transverse waves. Okay, this is the difference. Afterwards, we will take down all of these difference between transverse wave and longitudinal wave. You will take them down. If you are going to have any questions, that also part you can ask me. These are some of the definitions that are involved in case of longitudinal waves. Now see, at some points, the particles are going to be very close to each other. As you can see, this region of the waves. This region of waves is known as compressions. The region of longitudinal waves where the particles are close to each other. When these waves are traveling through the air, this region is going to be region of high pressure. The next part, rarefaction, is the opposite of this region where the particles are apart. Where the particles are apart, this is the region of longitudinal waves where the particles are apart, and if it is traveling through the air, then this is going to be the region of low pressure. These are some basic definitions that are involved for longitudinal waves. We are also going to have the definitions that are going to be there for transverse waves. As we know over here, the particles are vibrating up and down while the wave is traveling in the horizontal direction. And this, of course, the angle between them is 90 degrees. Now, of course, so these waves are going to be like this. The regions which are above the central line, these central line, when no wave is traveling, the straight line which I have drawn, the orange line that is being represented, that is known as the mean position. The region of the waves which is above the mean position, all of these parts, we call it crests. And obviously all the regions which are below the mean position, we call them troughs. Okay, so crest will be the parts of the transverse wave which will be above the mean position. Trough will be the part of the transverse wave which is going to be below mean position. What is mean position? That is also mentioned over here. Position of all particles when no waves are traveling. Okay, these are some of the definitions which are there, which you are going to take them down. If you have any questions, you are going to ask me, or else then we will proceed ahead. I'm going to pause this recording and you will take down everything. So this part I have already explained to you. In longitudinal waves, the direction of vibration of particles is parallel to the direction in which the waves are traveling. This is the direction in which the waves are traveling, and the particles are vibrating to and fro. It means left and right. And in case of transverse waves, you see the particles are vibrating up and down. Okay. And the direction in which the waves are traveling, it is along the horizontal direction. The angle between them, both of them, is 90 degrees. This is what is written. Direction of vibration of particles is perpendicular to the direction in which the waves are traveling. Yeah. So this is the part which is for the explanation. Compression, rarefaction. This part also you know. Wave front we will not do right now. That's what we are going to do later. These are some of the important definitions that we are going to take up. I'm going to first explain you all of these definitions. Yeah, this is the experiment which also we are going to discuss. This is the first experiment that we are going to take up. I have the video module of this, but at present I'm not showing it to you. I'll just explain you from here how we are proving that sound waves cannot travel through without material medium. So what we have done over here in this experiment is we have taken a bell jar. Okay, this is going to be an airtight bell jar, which means there is no leakage through it. There is an electric bell kept inside this. Okay, initially we will turn the switch on. We will be able to hear the sound of the ringing bell. The gong will be striking, the hammer will be striking the gong. The sound will be heard, and then slowly, with the help of vacuum pump, we are going to pull out all the air which is inside this bell jar. Slowly, slowly, as the air is being pulled out from the bell jar, the intensity of sound which is there, the amount of sound that you are able to hear, slowly, slowly decreases. At the time where almost complete vacuum is created inside this, you will be able to see that the hammer is striking the gong, but you are not able to hear the sound. It means sound cannot travel through vacuum. It requires material medium to travel. Some solid, some liquid, some gas has to be present. Then only sound will be able to travel through that. Therefore, it is an example of a mechanical wave. Basically, mechanical wave is that which will require some material medium, some solid, some liquid, or some gas. Then only it can travel. Otherwise, electromagnetic waves can travel even through vacuum. Light is a simple example. You can see from sun to the earth, there is vacuum in between. Nothing is present, but still light is able to reach to us. So electromagnetic waves do not require material medium. This part we will see later. Characteristics of sound waves. We will come back to this. Okay, these definitions we are going to take up. Now the first definition over here is frequency. Frequency, the symbol of frequency is small f, not capital F. Okay, it is number of waves produced in 1 second. Number of waves produced per second. The unit of this is hertz. The symbol of this is capital H, small z, hertz, Hertz. This is the symbol or unit of frequency. I'm just repeating that definition. Number of waves, how many waves are produced in 1 second. We are going to take some numerical examples also based on this. Okay, so that is frequency. The next part is time period. Okay, I'll come to this is the second definition which I'm coming. It is time taken by one wave to pass through a point. Okay, the unit of this is seconds. That's the unit of time. Frequency and time period, both of them are reciprocal of each other. So this is the first definition that you are going to take. This is the second definition you are going to take. Uh, you'll take down both of these definitions which I'm going to highlight, and then we'll solve some numerical examples after doing next two definitions. You can just take down both of these definitions. If you have any questions, you can ask me. You can also refer to open and refer to your textbook. That part also you can see. From there also, if you have any questions, we can look at from the notes also which you had shown me just now. If you're going to look into this diagram, this bell jar which is there, inside that, in the beginning here air particles are present at all these points. So at that time, sound will get transmitted through this air, and of course here glass is there, and outside also air is there. So here in that case, the sound is going to get transmitted. But as soon as all the air from this inside part, all the air particles are gone, there is empty space, there is vacuum. So there will be no material medium inside this space, inside this box that I have marked. So if there is no material medium, sound cannot travel through that part. Okay. Any other question you have? Okay. Which part? The previous part. Okay, this one. It is reciprocal of each other. The formula is given over here. F is equal to 1 upon T, or T is equal to 1 upon F. I'll give you one very simple example over here. Suppose if I say that the frequency of a wave is say 10 hertz. Okay, it means 10 vibrations are produced in 1 second. Okay, so the time period, how much time is going to get required for completion of one wave? It is simply going to be 1 upon F. So this is going to be 1 upon 10. This is going to be 0.1 second. It means in 0.1 second, a single wave is going to pass through a point. And 10 hertz, it means 10 vibrations per second will be taking place through that wave. 10 vibration means 10 times those particles are vibrating in 1 second. Okay. So this is how both of these are reciprocal of each other. Any other more questions you have, you can ask. Okay. You can take that part down, which is there on screen. The two definitions, frequency and time period. Also, you are going to write down that formula. I'm just going to highlight that part which you are supposed to take it down. I've highlighted everything, whatever you have to take it down.